So basically, such as trees, we like in the binary trees we have two nodes. Okay, so let's say there is a root, there is a left node, like left node, and there is a right node. Similarly, we have BSTs. Okay, but BST follows some specific logic, like how they are mapped. Okay, and we'll be talking about how it helps, how like how the data is arranged and how it is going to help us. Okay, let me go to the lecture. Okay, uh, not this one. Let's go to. So BST is binary search trees. Okay, so BST is basically binary search tree. Now one of the properties when we have a let's say a root. So we try to decide that the current data which we want to like make it as a left node or a right node is greater than the root or smaller than the root. Okay, so the all functionalities or traversal are similar to binary trees, except the way we try to arrange data in the tree. So all the smaller data comes at the left hand, and all the bigger data comes at the right hand. What do I mean by this? Okay, so let's open Jamboard and let's take an example. And also, like we already know that as of now that it's all recursion. So mostly the same traversal and all those logics would be same over here also. So yeah. So if I talk about a binary search tree, okay, binary search tree. Why do we name it search? That is also and very interesting concept behind it. So let's say that I want to create a tree with some given nodes. Let's have a pre-order of it. Okay, so let's try to have a pre-order. So I have this five. Then let's say that I have this. Okay, then this I have. Okay, let's say mm, then I have this and I have this. Okay, so let's say that this is a pre-order I am having. Okay, this is a pre-order I am having. I want to form a binary search tree. Binary search tree means, so whatever route I am having, whatever as a route I am having, the next part, the next node, I will check if it is. I will check if it is greater or smaller than my root. So I find that this is a smaller one, so that has to go on the left. Next root again, so I'll find that it is a smaller, so it's smaller than 5. Yes, it is smaller than 5. It's smaller than 3. Yes, it is smaller than 3. Then where to go? So next over here. Finally, next we have a 1. So 1 lesser than 5. Yes, 3. Yes, 2. Yes. So we have 1 at this one. Next I have 6. So I'll check that if 6 is lesser than this. So it will say no, then my 6 will be coming over here on the right hand side. So this is what we have, right? So the logic is a root is greater than equals to right, okay, and root is okay not equal to greater than, this would be just opposite. So right is either greater or equal to the root, and root is greater than the left one. So this is the rule we have to follow in binary search tree. Now we have 6 over here. Finally we have 5. So 5, no, then it cannot go left, right? Then it should come here. So it says that okay, so you are smaller, so you need to go this side. Then we have 7, check this, no. 6, no. So where to go left? So either go left or right. So we'll choose that. It will go over here. So this is how this pre-order traversal of the tree I have created a binary search tree. Okay, there is a question for you guys. Okay, the next question is, tell me what will be the in order. Okay, and is there any special thing within order? of BST. So tell me the tree in order traversal and what is the special thing with that. Guys. Okay. So what is the in order of this BST? Tell that. Guys, are you getting the point? What we are making? Okay, let me do it for you. So in order is basically we have the left, then we have the root, and then we have the right. Right. So if I go with one, so I have one as a left, then the root. Okay, then left, root, and then right. We have nothing. Then left is done, then root, then right, nothing at the right. Then left is done, then root, okay, then right. So right over here. Then finally left, okay, left, then root, then right, written, nothing else. So what is the like what is the good thing about this list? What is the feature? Yes, it's an ascending order, right? I hope you guys are getting the point. Okay, so in order of a binary search tree is always in ascending order. Okay, so it's always sorted and it is in ascending order. Okay, I hope you guys are getting the point. Okay, now why this search is written over here? Why this search is written over here? Let's see this. This is interesting. Anyone can explain why we call it binary search tree, not anything else? Why we call it a binary search tree? Okay, so the question is, the first question itself is search in BST. Okay, so search in BST. It says that given a BST and an integer k, if the integer k is present in the BST, find if integer k is given present in the BST or not. You have to return true if node with data k is present and return false otherwise. Assume that BST contains all unique elements. Okay, all unique elements are there. So we are getting the tree. Nothing. So we do not have to do the construction of tree. uh, then we have to search in the BST. So we have a tree something like this, and we have to search it. Okay. So what should I? So what should the code, guys, for searching? So one way is call in both the directions. Okay, call in both the direction, fetch the values, and that's it. For example, what I want to say is, I can say that if root equals null, then return false, right? It means that we do not find the number. Now, if whereas if root dot data equals whatever we are searching, then we return. Are you guys getting the base case? Okay. Now the point is, I can simply say something like this, that boolean left. Okay, the boolean left. So what would be a normal like if I want to search in normal binary tree? How, so what should be the code for that? Okay, so forget about binary search tree. I say that. if I have a normal tree, something like this, what should be the criteria? I want to find, let's say, two. Okay, in this tree, I want to find two. So what can be? What could I have done? Okay, and whenever I find it true, I yes, obviously I can do this. Okay, so the same thing. Okay, so I can simply say that search in BST and root dot left, okay, and the same thing for right. Let's just distinguish it. Okay, and I can simply say that left answer. What should be or and or right. So either we get true from left tree or either I get true from the right tree. So I will return this one. Make sense, guys? Okay. Why it says that cannot find symbol? Okay. It says that cannot find symbol. Left answer. Solution dot right answer. What is the issue with this one? Okay. Do you guys see any syntax mistake over here? Okay. Search in BST. This is the function, right? Solution dot search in BST. Then we have root comma k, and then finally call it. So it says that method error cannot find the symbol. Okay, leave it. I don't know like why I'm not able to execute it, but yeah, the point is we can do this. Okay, next part is okay. Thank you. Okay, I guess it will be running now. Okay, this is one thing. But the point is, what is the time complexity over here? If there are n nodes, so how many recursive calls are there? Any guesses? What is the time complexity? For finding true, or like for finding two, I made the left call. Okay, I was standing here, I made the left call. Okay, I made the right call. So left call to 3, then to 2, then 2 returned true, then 3 returned true. Okay, again this call went 6, then go to 5, then go to 7, finally false, false, return false, then return false, true, then false. So true, false, it will return true finally. But the point is, can I say that it is order of n here for searching? Okay, yes, if n is the number of nodes. Now, if I say that I am using a binary search tree, can I reduce this one? Can I reduce the complexity? How many of you say that yes, we can do that? Okay, try. So if Okay, all greater are on left side, right? Sorry, on the right side, right? So can I say that if my root dot data, if my root dot data is greater than, if my root dot data is greater than k, I do not, I just need this. Can I say this? So that's it. Nothing required. So k can only be found in the left subtree because it's a BST. Right will all. So if root is bigger, right is anyways going to be bigger. Make sense? Okay. And if not, then obviously like no other comparison required, I guess. And simply return this. So return, and if it is either equal, so it is going to return anyways. I do not need this also. So if it is greater than k, do this. Anything I'm missing? Let's see. I guess no. If you miss something, we'll check it. Okay. Getting the point, guys? Uh, okay. How many of you got this? Okay. See, the whole point of having BST is if I'm searching for 2 and it is a BST, why will I go here if my root is only 5? Okay, because these all are greater because it's right greater than root. So the only way to go is left. Now, if I am 3, so why will I be making a right call? No right call. Go left. And I find this, return, return. That's it. Over. The point is, what is the time complexity now? Correct. Correct. And what is log n basically? Can I say height of tree? Guys, okay. So this is the height of tree, right? So height of tree means, let's say there are 8 nodes. So 1, 2, 3, 4, 5, 6, 7. Okay, that's it. I guess. Yeah, like 7 nodes are there, but yeah, like the point is we have something like this. Okay, it will increase. So it is 2 power n minus 1 nodes means 2 power 3 minus 1. So what is the height? Height is equals to 3. If I take log n, so approximately base 2 to power 3 minus 1, approximately it is equals to height. Guys, okay. So approximately it is equals to height. Okay. So that is why we call it binary search tree, because search is optimized in this case. Make sense, guys? Okay. So we have optimized search. Adding deletion, that is order of n itself. ठीक है, वो order of n ही है अभी तक, but search है वो हमने optimize कर लिया. See, any data type, किसी भी data type, why do any data type exist? Either रीड ऑप्टिमाइज्ड है, आइदर राइट ऑप्टिमाइज्ड है, आइदर सर्च ऑप्टिमाइज्ड है, या फिर सॉर्टिंग ऑप्टिमाइज्ड है. सो ये सारी चीज़ें हैं. सो इन्हीं के बेस पे वी लर्न डेटा स्ट्रक्चर. ठीक है. सो एवरीथिंग वी आर लर्निंग टिल नाउ हैज़ टू डू विद डेटा स्ट्रक्चर्स एंड एल्गोरिथम कंप्लीटली. ठीक है. So why do tree exist? So why do binary search tree exist? Okay. Why do let's say why will we studying graphs? Well, be studying hash maps and all those kind of things. Okay. So there's a basic purpose they are fulfilling. Okay. Elements between k1 and k2. So print the element which is in range. Okay. Similar to our question. Okay. But yeah, anyways, you can just try this part out. So elements between k1 and k2. So you know that where we are searching for a range basically. Okay. Try that out. Okay. If else conditions are required. BST will be relatively very easier than binary trees. Okay, so the questions are more like since we have a restriction on the tree, so it becomes very easy for us to do this. So it says that binary search tree to a linked list. Okay, linked list. It says that given a BST, convert into a sorted linked list. What traversal should we follow for sorted linked list? Correct, very correct. We just saw that in order traversal of binary search tree is sorted in ascending order, right? Guys, okay. So given a BST, convert into a sorted linked list. Okay. So कह रहा है कि sorted linked list चाहिए. It means that we need to create nodes first of all. Okay. We need to create a nodes. For that help, we have been given this node tree, sorry, node class, which will be like picking up the tree node, and we'll try to form a linked list node. Okay. How to do it? Very easy, very simple. So in order traversal, okay. Okay, let's go step by step. What is the base case over here? Guys, yes, very basic, very basic. There's one more thing from your end. Like, how many of you have already done with the DSA part? And what about other guys? All of you are done. Okay, so WebD will start tomorrow. Okay, I guess maybe this month end we are will be finished with our DSA thing. So till when you will be like, okay, have you assigned to a group or like who is taking WebD? Okay, let me check. Okay, okay. Next step. What should be the next step in order traversal? So what do we need to do? Can I say that recursion? Okay, sorry, not recursive. Recursion. Let's recursion solve the problem. I'm standing at a root. I just only have to think about this root, nothing else. I'm standing at the root. Okay, let's take this diagram. BST to list. These are very simple questions, so do not have to worry about this one. Okay. The point is, I'm standing at 5. Okay. Now recursion is giving me answer. I don't know like what is that, but yeah, there's some answers coming from left subtree. There's some answer coming from right subtree. Okay, some answers coming from this side, some answers coming from this side. I'm standing over here. Can I see that whatever linked list I get from this part, I need the I what information I need here at this point in order to add this node to this node. Can I say that I need a head and the tail? Can I say that I need the both head and the tail? Let's say that recursion has solved this 2 3 4. So 2 3 4 is already done as a linked list. 6 7 8 is already done as a linked list. Now I am at 5. Can I say that this is head? I got the tail also. So can I say that left tail dot next is equals to root, and root next is equals to right head? Are you getting the point, guys? And what should I return? Which head and which tail? Yes, correct. Is the concept clear, guys? Uh, are you getting the point, guys? Right? Okay. So, like, nothing remains in the question. So, like I said in the starting also, everything is recursion. Once you are done with recursion, like really it becomes the same thing again and again. Okay. So let's create a class of node class. Okay, so I want to create a pair, and this pair which is a template. Okay, and similarly I will have this. So since we need a single or we need a double, so we need a double one. So we say that okay, but we do not have to do this. Right? We need just a object. So I can say that T of node. Okay, so T I can say that node one and T node two. Okay, let's create the constructor also so that I can simply return it. Public. Okay, public pair. Okay, node one, T node two. So generics, whatever you want to put at the place of T, do it. So this dot node one is equals to node one. This dot node two equals to node two. Okay, that is it, I guess. Nothing else. Okay, so let's create a pair. I will say that as pair, pair. What do we have? So linked list node integer. Okay, and let's make it this and new. Do you have anything? Yes, let's have this one itself over here, and should I add it? Okay, do I really need this? Okay, let me comment out. If I need this, I will just re-enable it. Okay, I do not want to save it. Okay, so we have the answer, but we cannot return a pair from here. So what I need to do is I need to create a helper function. So I'll say static, and then I will say pair and return this. Okay, I'll say helper. Finally, the only thing needed as of now is this root. That's it. Nothing else required. Okay, and we will be getting helper. per, okay, and the root. That's it. Return answer dot head head tail. That's it. So if root is equals to null, do this. Otherwise, pair. So pair left is equals to, okay. What should I write over here, guys? What will be pair left? Simple, the function call, right? No- Yeah, nothing. Yes, yes, that's it. That's it. So we have this pair over here, and then finally we have this pair left, and then pair right, and then finally I have this right over here. Okay, one more base case. Okay, for a leaf node, you just have to decide it. So and root dot right is equals. First thing first, create a node. Okay, so create a node. I'll say new node, basically new. Okay, and I guess we need to pass the data. So data should be root dot data. Okay, and finally return. Okay, let's activate this dot head and tail. So since variables are different, we do not use need to use this. But yeah, let's it be fine. No issues. I can simply say new. Okay. So head is okay. So if you have a single note, what should be the head and tail? For single node, head and tail is yes, very correct. So we have the same thing, right? Also, we have pair of this, so we need to write new pair of integer, and finally we have both head and tail as the node. Okay, so single node. If you have a single node, then we are just return it. So that is the head and that is the tail. That's it. Okay, and I guess we are almost done. So I will say that pair left dot next. We discussed that pair left dot next. Okay, so pair left dot. So pair left dot tail. Okay, so we discussed that left tail dot next. Okay, so left tail dot next will point to 5 and 5 next will point to right's head. Okay, so this will complete the cycle. Okay, the first thing. Second, node dot next is going to point to pair right. Okay, the pair right dot head. Pair right dot head is what it is pointing. What should be returning, guys? What we should be returning? We just discussed it. Okay, the head would be of, yes. So you just need the head left and the tail of right. So we need the pair uh, right dot tail. That's it, I guess. Okay, so let's check for once. So we created a pair with this T, the template. Okay, the head is there, the tail is there. Then we have this pair constructor. Next, we created a helper function. So we say that if we have a root null, so return null. Otherwise, do this. So we can remove this part. We do not need exactly. Okay. Now we are creating, we are getting a pair from here. So we am saying that helper root. Now whenever my root reads here, so if it is null, so return null. That's it. No comments. Otherwise, if root dot left is null and the root dot right is null, it means that we have a leaf node. So it is very straightforward. Create a new node with the root data. Okay. Create a new node with the root data and simply return at head and tail because it's the same thing. Then we pair left whatever linked list we are getting in here and whatever we are head and tail we are getting over here. So pair left dot tail dot next will be node. Okay, so pair left dot tail dot next will be node, and node next will be pair right head. So just creating the link. Okay, and finally what to return is the pair left head and the pair right tail. So we are returning this. Okay, so I hope this is clear. Okay, let's run this and check out if we are on the right track. It says that pair is public, should be taken in a file. Okay, it says that cannot find symbol node 2. Okay, makes sense. Very correct. Capital 1 and yeah, it says that cannot find symbol. Okay, node is not found. Why is that? We have node over here itself. Okay, so okay, obviously. So this should be out over here also. One node should be here also, right? Hmm. So we are getting some issues and some are fine. So why is that? Let's check. -1. Ah, okay. So null pointer exception. What did we miss, guys? Okay, let's apply our logic on this one. So we have 11 minus 1, 12 minus 1, 13 minus 1, 14 minus 1, and 15 minus 1. Okay, let's try to form the tree. So, and obviously the order is basically pre-order, right? So we are getting this in. So pre-order. Okay, so contains the data of the node. The data of the data is separated by. So, so okay, is this running or this also failing? So 46, 44, 43. Okay, so 46. So pair left dot tail dot next. Okay, is equals to. Okay, so pair left dot tail dot next equals to node null pointer exception because tail is null and we are trying to access the next of it. But how did this happen? Uh, okay. Okay, obviously. So this is one case. One case can also be that I if if pair left is equals to, okay, so let's see this also, that if pair left is null, okay, then it means that only right subtree exist, ठीक है, सिर्फ right subtree अगर exist करता है, then in that case what should be returning? I need this, okay, and for returning I need this. So it means that we do not have any right subtree. Okay, right subtree exists ही नहीं करता. Then in that case, we have to, sorry, left tree exists ही नहीं करता. Then we just have to do next, like node dot next and pair right dot ahead. If it is null, then it's totally fine. Okay, so node next null हो जाएगा. So single node is there and it will be satisfying the condition. But the point is, key, what should I be returning here? So now I do not need to return the head. I can simply return the node because there is nothing in the left, but we have something in the right. So that is to be written. Similarly, if there is only left subtree, okay, right subtree is empty. So if we have the right subtree as empty, then only this is true. Do not need this, so only left subtree and the node, so that is it. So pair left dot head and the node. Otherwise this is totally fine, right? Okay, let's run it again. So there is only one failure, which is this case. Let's try to solve this also, guys. Are you getting the conditions, uh, guys? Okay, so this is saying that कि अगर left subtree है नहीं, so it means that only we have to deal with the right one. ठीक है, तो फिर head is the current node, ठीक है, बाकी that will come in the right. And if there is no right subtree, so node is the tail, ठीक है, node is the last node. But this one is for -1 case. Okay, so what is missing? I'm doing this right. That if root is null, please return a null. And oh, okay. So since we are returning a null, then answer dot head will be null. So I can say that if answer is equals to null, return null. Okay, make sense? Because there will be no head of null. Okay, so ठीक है, like the questions are like doable. Not that if we have anything bigger over here. Okay, this is also a very easy one. So it says that lowest common ancestor of binary search tree. Lowest common ancestor. Lowest common ancestor means um, the lowest parent. Okay, the lowest parent. So it says that given a binary search tree and a data of two nodes, find lowest common ancestor of given two nodes in the BST. Of given two nodes in the BST. So lowest common ancestor of two nodes A and B is the lowest or deepest node which has both A and B as its descendant. The like with has both A and B as descendant. Lowest one. Let's say that it is saying for A and B. So is A and B descendant of this one, the first node? Okay. For green. Okay. So I need to find this one. So what should you do? What should the approach? So what can be done? Can I say that? Can I say that uh, at a right, at a right, I know that both the nodes will fall in left if both are smaller than right. Are you getting the point? Both nodes, if are smaller than uh, root, they will fall in left, and if it is bigger than it, they will fall in right. Make sense, guys? Okay. So if you carefully see, we are searching for a junction where both nodes get separated. One is in the left hand and one is in the right hand. That is the my that route is my answer where the separation is happening. Are you getting my point? Because when there is a separation of these two nodes, no descendant can happen. This is not a descendant because these two are separated now. Make sense, guys? Are you getting the point? At this route, A comes at left, B comes at right, or vice versa. Like B comes at left and A comes at right. Then this route is my answer. Otherwise, if both falls in the same either left either right, that is not the answer. For this one, this is not the answer. I need the lowest. Okay, highest is the root. Highest is the root. That is not the question. The question is lowest. So lowest will be which is at the end one. Are you getting the point, guys? So can we say that if we have a left call, we have right call, and there is a if condition, if this A is greater than root B is smaller, and if B is greater A is smaller, then return a root, and that is the answer. Okay, very easy one. So what is the example? Let's take on. So 8, 5, 10, 2, 6. 8, 5, 10, 2, 6. Now what they want to find? They want to find 2 and 10. Okay, like 2 and 10 is like they already have it here. So let's say that I want for 2 and 7. I'm searching for 2 and 7. So I come here, I check that 2 is also less than 8, 7 is also less than 8. No calls on the right. All the call goes to left. Now I come over here, I again check it. So one of the value is greater than this, and one of the value is smaller than this. Can I see that I return 5? Yes. Okay. So that's it. I guess this will be our answer. 7. So return this. That's it. Nothing from here. Nothing from this side. Maybe return a minus infinity. So minus infinity 5. Anyways, it is going to be So whatever be not equals to minus infinity, that is our answer. Done. Will it be like solvable, guys? I guess. Okay. Okay. Let's do one more and like gets done with this lecture, and let's will be getting started with the next one tomorrow. So replace with sum of greater nodes. Okay. Replace with sum of greater nodes. It says that given a binary search tree, you have to replace each node's data with sum of all nodes which are greater or equal than it. Okay. Either greater or equal than it. You need to include current nodes data also. That is, if in a given BST there is a node with data 5, you need to replace with some of the data and all nodes whose data is greater than or equal to 5. Greater than or equal to 5. Okay. Either greater or equal to. So it says 8, 5, 10, 2, 6, 7. Then we have 2 minus 1s. Okay. And something. This is a good question. Okay. Replace with sum of greater nodes. So we have 8, 5, 10 to 6. We are at 8, right? So we are at 8, and then we are at 8. Okay. So I want to replace all the ones with greater nodes. Now, rightmost node will not change. How many of you agree with this? Replace with sum of greater nodes. ठीक है, जो नोट्स बड़े हैं उनके नोट से इनको रिप्लेस कर दो. You guys agree with this कि ये like this will be never be changing, right? Because this is the greatest one of it. Yes, yes. Now let's increase some complexity over here. Okay. Now 11 will never change. Okay, 11 will never change. But the data I return from here is I need to return this. Okay, I need to return this to 10. Okay, I need to return this to 10. So whatever I get from the right data, okay, see this. We need to observe this one, that whatever we get from right, recursive call, first call is right. Okay, remember, first call is right, then we'll go left because we need the greater node sum. So no left call, only right call first of all, then we go to left. So right call, then this right call returns a sum, then this right call returns a sum. Okay, then I go to okay, then I have to go to this 9. Okay, then I have go to this 9. I will say that uh, also whatever I have the sum from here. Okay, how to suppose with this? So we have this sum, then I need this data and this data too. Okay, so I require both of it. So this 11, and I can switch it to this one, right? And I need to return the uh, left sum. Okay, I need to return the left sum. Okay, so returning 11 to this, And should I change it now itself? So if I compute it, so whatever root data I'm having, plus this one, so I will make it a 21, and I need to supply this 21 to 9 somehow, and this 21 will receive at 9, and 9 will return 30, and this 30 will be only what is going to be returned. So if I summarize, I need to return every time the left sum. Every time I need to return the left sum. From here also, the left sum first. But the order of traversal will be, we will go to right first. Okay, because we need the greater nodes. And that is the reason we'll go to right first. Let's figure out this one. Okay, then we'll figure out later. So first thing first, what do we need to do? We need to replace with it, right? So we need to replace with that. So first thing first, can I need to? Do I need it here also? Okay, let's create a helper function first. Then we'll think more. So I will say that helper function will have two things. First of all, current sum. Okay. First of all, the root and the current sum. So I'll say static int helper, and it is a binary root over here. Then we have int sum over here. Now, if root is null, straight and simple, that is it. Nothing else is required. Okay. Now, as what I said, like I need to go to right first. Okay, we need to go to right first so that we get all the greater sums. So that is the reason I will go to root dot right, comma whatever sum it is. Okay, and I will bring the right sum. Now my current root. Okay, so what I'm doing, whatever I'm getting from the right, I am adding to myself. Okay, so I'm updating myself. Whatever I'm getting from right, I am updating myself. So root dot data is no more root dot data, it is going to be root dot data dot right sum. Do you guys agree with the first and the second step? Okay, let's pay attention. So first is the right sum. Okay, I need to replace all nodes with sum of greater nodes. जो भी nodes बड़े हैं उनके सारे के sum को current डेटा को, जो भी करंट डेटा है, दैट हैज टू बी रिप्लेस्ड. इसीलिए आई एम गोइंग टू राइट फर्स्ट. जो भी राइट से डेटा आ रहा है, आई एम कैप्चरिंग इट, अपडेटिंग माई सेल्फ. ठीक है, अपडेटिंग माई सेल्फ. सो आई वेंट टू एक्सट्रीम राइट. जो भी डेटा मिल रहा है, रूट डॉट डेटा इज इक्वल्स टू रूट डॉट डेटा प्लस राइट सम, वट एवर द राइट इज गिविंग. आर यू गाइस गेटिंग दिस पॉइंट? Guys, okay. Now, see this. See what is going to happen when we go to left. Now, this left call needs a right data also and the root data also, because these both are greater than left. So, इसको ये डेटा भी चाहिए, ये डेटा भी चाहिए. So, it needs the sum of these two. Make sense, guys? Guys, okay. So, the next calls come something like left sum is equals to helper Let's left sum is equals to helper, okay, comma root dot uh, left. I'm going to left, okay, and the sum should be, what should I pass here, guys? So left needs sum of both root dot data and right sum. You guys getting the point? Correct the root data plus the right subtree sum. Make sense? Guys, okay. And finally, what I return here is the left sum, which I'm getting. Okay. So I go to right, I go to extreme right. Okay. So let's just summarize. So the idea was go to extreme right, this right. Okay. Finally, uh, what I'm doing is this is zero, this is zero, this is null, so null is returning zero. So right sum is returned as zero. Okay. So calling to extreme right, right sum is returned to zero. Current root dot data. Okay, it is root dot data plus right sum. It means that 11. So root dot data dot right sum, and it is 11. Go to left, go to left with the updated data. Again here 0. Okay, so getting 0 from this side. Okay, so am I going to update it, or what do I return? So if I call on the left side, if I call on the left side, so it is 0, right? And it will tend to return the same thing, whereas I want that whatever went, okay. So this is for this node, we need to think once that should I return for the leaf node? No, I shouldn't do that. Leaf node, I need to think that if 11 is there, so I'm going to this place and I'm returning a 0, which is being added, updating myself. But when I call in the left direction, so for left it is a bit tricky, so I need to think how do you update this part. So for left sum, I made a call, and that node will update itself with the sum. Okay, so we are passing the sum at this point, and whatever is returned from the left hand side, that is what will be returning. So we are passing 11, and that is what we are going to return. Okay, so let's see what we are passing. So we are passing 11 and as the sum. So 11 is passed as the sum, and since that is returning us a 0. Okay, so we should, instead of returning 0, we need to return the sum over here. Okay, I guess we figured it out. So instead of returning a 0, I need to return the sum. So let's say that I transferred 11 over here. So I need to get back 11. Okay, if it is 0, then finally I will make this call from the right subtree. Okay, So this sum is the root dot data, like the right node plus root data I am sending to the left tree. Now if left is null, so it should return the same thing back without any like zero or something, so it should return me the same thing. Okay, so if it is null, so left will return me the root dot data itself, and I can transfer it to right call. Why I did this return sum? Is it getting clear, guys, or should I explain it once? Is the return sum clear? Okay, it's because if it is null we'll get a zero, but that is not true. Okay, because what we pass here is that to be counted. So let's see if we are on the right track. Okay, so we are on the right track, right? So let's submit it. So that's it. This is like a 3 4 line solution. That's it. Are you clear with the solution, guys? What is the traversal here? Any guesses? What we call this traversal? Reverse in order. Okay, are you guys getting the point? What is in order? Left, root, and right. And what is here? Correct. So basically, it's the everything like already have said so many times. You know that what's it? Just once you are once you like learn recursion, you are a smarter person, right? That's it. No more comments. Okay. I hope you guys are like enjoying solving the recursion. Okay, because everything is recursion. So today is second. So yeah, obviously a new journey for you will start tomorrow, the WebD part. So how many of you have already done WebD, guys? Any similarity, familiarity, and experience? Class 8th, right? Oh, okay. Yeah, don't worry. Like, CSE guys, just uh, I gave exam for just passing, so no more difference. Like, um, hey, the point is, ki, whenever you write the code now, there's something visual, like you see something, right? That okay, paragraph is coming, colors are coming, but थोड़ा सा रंगीन है वो, and DSA is not रंगीन. Okay, so yeah, but the like it will be fun. It will be fun. Okay, so let's complete this DSA fast so that you people like it doesn't bore you more. Okay, and you get sufficient time for revision. Okay, guys, let's meet tomorrow at the same time. Thank you. Bye.